Thank you all for joining us today for this first talk of the third season of the IGCP648 virtual seminar. And today we have Dan Brennan, PhD student at the Earth Dynamic Research Group here at Curtin University, and he will present Reconciling paleogeography reconstruction with the record of Rodinian rifting in the northwestern United States. So Dan, if you're ready, the audience is all yours.
All right, great. Thanks for the introduction, Luke, and thanks to everyone from all over the world for tuning in. So as Luke mentioned, today I'm going to be talking primarily about new results from my PhD that were recently published in geology. And I wanted to acknowledge and thank some of my co-authors, including my PhD supervisors, Professor Lee, Paul Link, and Tim Johnson, along with many others. So yeah, this talk is based primarily off our recent geology paper, but I hope you don't mind that I also include a quick shameless plug for two other of my recently published papers that are related to the same topic of Laurentian rifting, including a 2020 tectonics paper and a 2021 Terra Nova paper. So as probably most people in the talk are familiar with, we know that the cyclicity in the Earth's tectonic record is well documented. And one of the longest tectonic cycles, the supercontinent cycle, postulates that about every 600 million years, the majority of the Earth's continents assemble into a relatively singular landmass. The prevailing wisdom is that this has happened at least 3 times throughout Earth's history, with Pangaea, Rodinia, and Columbia or Nuna. So this talk is focused primarily on the Neoproterozoic supercontinent Rodinia and how our new results from Laurentia impact our understanding of Rodinia assembly and breakup. So the regional geologic record of Laurentia has long been recognized as integral for Rodinia reconstructions, and Laurentia is usually featured near the center of the supercontinent Rodinia for some reasons we'll get into in a bit. And this is Laurentia here at the center of the Rodinia reconstruction from Mitchell et al. 2021. So generally the assembly of Rodinia is marked by globally widespread 1.3 to 1 billion year old orogenies. And Laurentia probably contains the most well-known origin of that age, the Grenville origin, which affected most of eastern Laurentia, shown in brown here. The occurrence of a similar age western Grenville event has been hinted at based on some geochronology results, primarily within metasedimentary rocks of the 1.4 GA belt basin that are mostly interpreted to date enigmatic metamorphic and mineralization events, but no igneous rocks of Grenville age have been identified in Western Laurentia. And generally, it's my impression that there's not a consensus in the Laurentian geologic community on the credibility of a Western Grenville event. The breakup of Rodinia and Laurentia is marked by the intrusion of the 780 MA gun barrel dikes and culminates with early Paleozoic passive margins that fringe Laurentia along the eastern or Iapetan margin and along the western and Cordilleran margin associated with the opening of the Iapetus and Paleo-Pacific Oceans. So since this seminar is for IGCP648 supercontinent cycles, I thought I'd bring it back a little bit to the basics of how do we reconstruct a supercontinent. So I think we all know that it takes a multidisciplinary approach, and various geologic events or aspects must be considered and investigated, such as basement provinces, orogenic histories, basin histories, paired rift margins, plume events, plate kinematics, paleomagnetism, and I'm sure there's a few more that I missed. Now, some of these events might tell us different things about the supercontinent process. For example, orogenic histories and basin histories might reveal more about assembly of a supercontinent, while things such as paired rift margins and plume events might give us more information about the breakup. Now, I borrowed this kind of figure or idea from my supervisor, Professor Lee's kind of famous 2008 paper. And I really like how in that paper they describe the study of these various different geologic events or aspects can be thought of as one line of evidence. So for example, the paleomagnetic record might give one line of evidence. However, when only one line of evidence is applied, as is sometimes the case in geology, it's difficult to find one unique solution, and there are often several answers that could follow along a single line of geologic evidence. So consequently, it's not really until we have lines of evidence emanating from all these different aspects and they intersect at one point that a credible solution to reconstructing a supercontinent or a paleogeography can be reached. So as my title indicates, this talk is focused on the record of Laurentian rifting in Rodinian rifting in Western Laurentia. So to get us started, I'm going to introduce a little bit of the regional background and highlight some disagreements in these so-called lines of evidence for Western Laurentia that were critical in developing our understanding of Rodinia. So Stewart in 1972 was probably the first to recognize that the western margin of Laurentia records a Neoproterozoic continental rifting event. And this paper was a bit before my time, but in many ways, almost 50 years later, Stewart's original suggestion of a continental separation between 850 MA and 570 MA appears to be impressively close to the mark. As our understanding of the Neoproterozoic stratigraphy in Western Laurentia and elsewhere improved, a South Australian Western Laurentia conjugate margin reconstruction was proposed by Bell and Jefferson. While this correlation was mostly based off lithostratigraphic similarity, it was also consistent with some very early paleomagnetic constraints. And eventually in 1991, perhaps the first complete or mostly complete attempts at a Rodinia supercontinent reconstruction were published in 3 landmark papers here, one shown by Moores and another by Hoffman and Ian as well, who is in our talk, so that's pretty cool. And all papers showed similar configurations between Western Laurentia, East Antarctica, and Australia as conjugate margins. And this kind of configuration has subsequently been known as a SWET, or Southwest US East Antarctica connection or configuration. Early on, many of these reconstructions suggested that this configuration was relatively stable starting from about 1.8 GA and existed until as late as 780 MA. A time span that we now think actually spans 2 supercontinents from the Paleoproterozoic Nuna and Columbia supercontinent to subsequent supercontinent Rodinia. However, various other reconstructions have also been proposed since this time, including one of the leading models originally featured in Lee et al. 1995, but which was more or less similar with the model that resulted from the IGCP648 Rodinia reconstruction of Lee et al. 2008. This model emphasized some of the issues with Australia and Antarctica as direct conjugates with the western margin of Laurentia, and suggested that South China, right here, may have been the important missing link between Australia, Antarctica, and Laurentia within Rodinia. Importantly, this missing link model requires that the relative Laurentia, East Antarctica, Australia configuration was achieved through a Western Grenville age orogenic event that is recorded in South China and marks the assembly of Australia, Antarctica, and the Yangtze block of South China with Western Laurentia and the Western Laurentia associated Cathasia block of South China along a convergent or subduction boundary. However, others continue to favor a sweat-like reconstruction, such as this recent one by Meredith et al. In Earth Science Reviews. In this model, instead of a convergent boundary along the western margin of Laurentia here, they favor assembly of Rodinia along a large transform structure. And just for fun, I overlaid the original sweat configuration to show how similar these configurations are, published 30 years apart. So although these are only two of perhaps too many models for Rodinia reconstructions, both ideas continue to be highly cited, and it's my impression that it'd be hard to say that one is more widely accepted than the other. And so useful models are testable models, and what better way to test or evaluate these different competing models for Rodinia paleogeography and Rodinia reconstruction than to investigate the relevant regional geologic record, right where all the action was allegedly happening along the western margin of Laurentia. So that is what I did for the majority of my PhD work so far, and the stars here highlight the general location of my study area in the Priest River region of Western Laurentia. So if we zoom in on the western margin of Laurentia, shown here, the work of many Cordilleran geologists was very well presented in Yankee et al. 2014, which probably remains one of the first papers and favorite papers I was assigned to read at the start of my master's work. But in this paper, it shows that along most of the Cordilleran margin, 770 MA or younger rocks unconformably overlie 1.4 GA or older rocks. Specifically in the Priest River region that I was studying, these 1.4 GA rocks are comprised of the Belt Purcell supergroup, which yield very important constraints for supercontinent Nuna or Columbia, but generally they are too old to help us constrain Rodinia processes. And the unconformably overlying rocks of the Windermere supergroup can help us constrain Rodinia breakup processes. But this begs the question, where are the potentially expected 1 billion year old rocks in this region that might record or help us constrain the record of Rodinia assembly? So one particular sequence in northwestern Washington state may yield some important clues to this question. In this region, a major regional thrust fault, shown here, the Jump Off Joe thrust fault, separates two sequences of strata. In the eastern footwall are rocks of the 1.4 GA belt supergroup, shown here in green, while in the western hanging wall are rocks of the Deer Trail group, shown here in orange, the Buffalo Hump Formation in blue, and overlying rocks of the Windermere supergroup in purple. And I should note that at the time these correlations were made, the Buffalo Hump Formation was considered the uppermost unit in the Deer Trail group, but that has since been revised. So based on earlier lithostratigraphic correlations across this thrust fault, the Deer Trail group, including the Buffalo Hump Formation, were correlated to belt supergroup strata to the east in the footwall of this thrust fault. So based on this correlation implied that the Buffalo Hump Formation must coarsen or coarsens to the west, and presumably would be consistent with having a western non-Laurentian source region based on the correlation of these different stratigraphic units across that thrust fault. And I should note that also At the time that this correlation was made in 1989, the depositional ages of both units are very poorly constrained. So subsequent early detrital zircon geochronology from the Buffalo Hump Formation showed that it contained 1.1 billion year old detrital zircon grains, which suggested a Western source of Grenville age grains into the Buffalo Hump Formation. Now, this interpretation made by Ross and others in 1992 has featured strongly within certain Rodinia reconstruction models, such as the missing link model, which suggests that the 1.1 GA orogeny in South China was located along the western margin of Laurentia during the assembly of Rodinia. As shown by Yao and others in 2017, in this revised version of the missing link model, the 1.1 allegedly western derived detritus within the Buffalo Hump Formation was sourced from the Sabao origin in South China. So this leads me to the research question that we're investigating in this talk. What is the depositional age and setting of the Buffalo Hump Formation? Is it a unique 1 billion year old deposit, likely from a Western Rodinia forming collision? Is it potentially a younger deposit, likely formed during Rodinia rifting? Or are there other possibilities, such as the early detrital zircon results might have had some issues? So for the non-North American geologists, and just for fun, I thought I would introduce where the name comes from. So buffalo is really the cowboy name for the American bison, which I just looked up. The scientific name of the American bison is bison. And these once roamed all over North America. And so apparently to the early geologists in the region, the topography of this hill, which the formation in question crops out on, was remarkably similar to the hump on the back of a bison or a buffalo. So that's where they got the name Buffalo Hump Formation. So Box and others published some detrital zircon results from the entire Meso to Neoproterozoic sequence within the Priest River region just recently in 2020. So that was a nice foundation for my results to build off of. So Box's work showed that the units of the Deer Trail group below the Buffalo Hump Formation lacked detrital zircon grains younger than 1.3 GA. And consequently, they were not a Grenville age deposit, and they are older than the overlying Buffalo Hump Formation. They also showed that the Buffalo Hump Formation contains many 1.1 GA grains, and the original correlation of the Buffalo Hump Formation to the 1.4 GA belt supergroup on the east of the fault is incorrect. Consequently, considering that the coarsening westward interpretation for the Buffalo Hump Formation mostly relied on the incorrect correlation across that thrust fault, the original premise that it required a western source was no longer supported by Box's work. So we went in and took a detailed look at the Buffalo Hump Formation, including measuring some stratigraphic sections. And it's actually predominantly a mudstone unit, but in certain discontinuous interval sandstone beds, intermittently coarsen upwards, sometimes as coarse as into conglomerate. And overall, the sandstone intervals decrease in thickness and coarseness up section. The clasts were almost all predominantly quartzite, and while paleocurrents from cross beds in these sandstones were difficult to measure, they generally suggested west to northwest paleoflow direction. The detrital zircon results from the Buffalo Hump Formation. First off, we have results just from the sandstone facies, and then results from an individual cobble. So the detrital zircon results from the sandstone facies show a range of 1.0 GA and older sources that are consistent with sourcing from the Grenville origin in eastern Laurentia and interline Laurentian locations. So our analysis of an individual quartzite class from the conglomerate indicated that the class were likely reworked from the underlying deer trail group. Our initial sandstone analysis from 4 samples also found 2 760 MA grains. So to get a better constraint or evaluate these 2 young grains as a possible younger population, we utilized a rapid laser ablation methodology, which allowed us to scan another about 1,200 grains in a couple hours, and we returned, did a returning analytical session to retarget the probable young grains with a robust full analysis spot. And overall, we got 28 robust analysis dates on these young grains from all 4 different sandstone samples, which give a Concordia age of 758 plus or minus 7 MA, which we interpret as the maximum depositional age of the Buffalo Hump Formation. As this 760 MA unit unconformably overlies and reworked 1.3 GA units, it appears that the first influx of 1 billion-year-old detrital zircons into this region occurred after 760 MA. Based on the stratigraphic and detrital zircon results, we interpreted the Buffalo Hump Formation to record localized rifting after 760 MA in this region. Considering that the Buffalo Hump Formation and Deer Trail group rocks are not present to the east or on the footwall of this Jump Off Joe thrust fault, we suggested that this regional thrust fault is a reactivated Neoproterozoic normal fault that was active during the deposition of the Buffalo Hump Formation and reworked Deer Trail groups on the eastern footwall block into the adjacent hanging wall Buffalo Hump Formation basin. And I suggested the distal Grenville age, or the Grenville age grains in the Buffalo Hump Formation had a distal provenance in eastern Laurentia, and they were likely sourced by transcontinental river systems similar to the ones similar to other ones proposed by researchers such as Robert Rainbird that drain the Grenville origin and span the width of Laurentia. So consequently, this suggests that the first occurrence of localized rifting was no earlier than 760 MA in the Priest River region. Similar age basins are present elsewhere along the Laurentian margin, but they are relatively localized and seem to correspond to pre-existing crustal boundaries. Notably, all of these basins lack detrital zircons between the ages of 900 and 780 MA, consistent with a period of stability in Western Laurentia due to its position within Rodinia at this time period. So consequently, our results indicate that the Buffalo Hump Formation was deposited during Rodinia breakup after about 760 MA, not during Rodinia assembly at about 1.0 GA. Generally elsewhere along the margin, the 780 to 540 MA rocks are interpreted to record a single prolonged rifting process with continental separation not occurring until about 540 MA. Here, Boronic draws comparisons between this prolonged Neoproterozoic rifting process in Western Laurentia and the shorter but perhaps similar process during the opening of the modern North Atlantic Ocean. A comparison I argue holds true along the western edge of the Belt Basin in my tectonics paper. And importantly, to bring this back out to the big picture, both the discussed missing link and sweat Rodinia models favor Laurentian conjugate margins either in South China or Southeast Australia. And both in South China and Southeast Australia have rifting and volcanism prior to 760 MA. And I believe it occurs as early as 850 MA in South China and perhaps as early as 830 MA in Southeast Australia. There is no record of rifting or volcanism of this age in the Priest River region. Additionally, both the sweat and missing link models suggest continental separation occurred along Western Laurentia by about 720 MA. In most Cordilleran geologists' perspective, this is just when rifting started and long before oceanic spreading occurred along the western margin of Laurentia. These issues led me to speculate that perhaps the earlier 780 to 720 MA basins in Western Laurentia, which now include the Buffalo Hump Formation, record one rifting event, while the classic prolonged rifting event is recorded by the less than 720 MA Windermere Supergroup strata, suggesting that perhaps there's actually two rifting events along the margin of Western Laurentia in the Neoproterozoic. And this is not a completely new idea. Others have proposed similar scenarios, such as Kolperen and others in 2002. So just to recap and summarize our results, while models such as the missing link may be paleomagnetically permissible, the fact that the Buffalo Hump Formation is not a 1 GA deposit, and instead there are no 1.0 GA strata in this region, would suggest a shortcoming in what the missing link model would predict. On the other hand, while sweat models may also be permissible based on the paleomagnetic data, there also appears to be a discrepancy or complexity in the rift margin history if Western Laurentia and Southeast Australia are viewed as simple conjugate margins. So perhaps the lines of evidence are converging towards a different solution than the one favored by either the missing link or the sweat model. And other models have been recently published besides just the sweat or missing link models, such as this one by Eister and others in 2020, which is similar to the original OSMEX configuration, if you're familiar with that. However, in their reconstruction, they also acknowledge that this reconstruction also has some issues with the record of rifting in Western Laurentia. And I think they say it more eloquently than I could have, so I'll just reread their excerpt. The second complication is the existence of a linear and long-lived rift margin along Western Laurentia. However, this issue is a limitation of all previously proposed models. It is possible that there were several continental fragments in combination along the margin. In some cases, these fragments could have continued to disintegrate and subsequently be accreted to various cratons. As discussed below, the long-lived rifting likely reflected a much more complex history than a simple rift margin that initiated at 720 MA and continued until the Cambrian. So in my concluding remarks, I hope we at least can all agree on the first 2 points that I'll cover here, that multiple intersecting lines of geologic evidence are needed for credible paleogeographic reconstructions. And in particular, I think this study shows that regional discrepancies, such as the simple correlation of strata across a regional thrust fault, can have big picture implications for global reconstructions. And I think our work in the Priest River region has indicated an absence of Granville Age sedimentation, or at the very least, an absence of preservation of that sedimentation. Although there is perhaps an enigmatic Granville Age metamorphic event. An earliest onset of rifting at 760 MA, and essentially complete tectonomagmatic quiescence from about 900 to 780 MA in this region. And it is my rookie opinion that these lines of evidence do not clearly intersect with the leading sweat or missing link Rodinia reconstructions. With that being said, I just wanted to end with a picture of some cool Native American petroglyphs from the field in northern Idaho. And whenever I come across these, I always think it's a cool reminder to us that as geologists, we're probably not the first people to find meaning or significance in the rocks we study. So thanks for either staying up late or getting up early to tune in with me. And I'm happy to talk about any questions we might have. Thanks.